The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Our lecture today concerns mathematical induction, which roughly speaking is a technique that one uses to prove something when one already has a pretty good suspicion as to what the right answer is. Now, rather than to philosophize about this too long, let's tear right into a problem and see in action just what the concept means. Recall that in an earlier lecture we have proven that the limit of a sum is equal to the sum of the limits, provided, of course, that there are only two terms in the sum. That is, if we have two functions f1 and f2, the limit of f1 of x plus f2 of x as x approaches a is the limit of f1 of x as x approaches a plus the limit of f2 of x as x approaches a. The question now is, how about the limit as x approaches a of f1 of x plus f2 of x plus f3 of x? Now, to tackle a problem like this, we do what is so often done in any mathematical logical procedure. We try to reduce an unfamiliar problem to a familiar problem which has already been solved. Let's see what I mean by that. If this had been only two terms in here that we were adding, we would have known how to handle this problem. So what we observe is that since the sum of two functions is again a function, we can assume that our expression is written this way. Now you see we've reduced our problem to the sum of two functions, namely f1 of x plus f2 of x being one of our functions, f3 of x being another of our functions. We know now what? That the limit of a sum is the sum of the limits if we have two functions. You see, this is what? The limit f1 of x plus f2 of x, you see, plus the limit as x approaches a, f3 of x. But now look what's in this expression over here. This is now what? The limit of the sum of two functions. And you see, we know that the limit of a sum is the sum of the limits is true if we have only two functions. So from here we get to here, and from here we can say what? This is the limit x approaches a, f1 of x, plus the limit as x approaches a, f2 of x, plus the limit as x approaches a, f3 of x. In other words, what we have shown is that the limit of a sum equals the sum of the limits is true not just for the sum of two functions, but for the sum of three as well. And more importantly, the truth for three hinged directly on the truth for two. In other words, it wasn't just that we proved that the formula was true for the sum of three functions. We proved it on the assumption that it was already true for the sum of two functions. And by the way, notice how we may now begin to suspect that this idea generalizes. For example, let's take a look over here. Suppose I now said, how about the limit as x approaches a, and we'll now take the sum of four functions, f1 of x, plus f2 of x, plus f3 of x, plus f4 of x. See, what about something like that? And again, we argue the same way as we did before. We say, you know, if we had only had two functions in here, and this gives us the hint to do this, see, we do know that the limit of the sum is the sum of the limits if we have only two functions. You see, now I could write this as what? It's the limit of the first one as x approaches a. But what is the first one? The first one is the function f1 of x plus f2 of x plus f3 of x plus the limit of the second. The second now you see is f sub 4 of x as x approaches a. Now you see our previous case told us what? That the limit of a sum is equal to the sum of the limits if you have the sum of three functions. That's exactly what we have over here. And now you see we can say what? This is the limit of the first as x approaches a, plus the limit of the second as x approaches a, plus the limit of the third as x approaches a, plus the limit of the fourth as x approaches a. In other words, what have we done now? We've shown that knowing that the limit of a sum is the sum of the limits was true for a sum of 2 functions and of 3 functions. We've shown inescapably that the same result holds for the sum of 4 functions. Let's take a little breather here and make a few asides. I think sometimes when one starts to work too much with mathematical symbolism, we lose track of the fact that things are not quite as difficult as they might otherwise have seemed. You see, for one thing, my claim is that we have already tackled this problem as recently as first grade arithmetic. Namely, we learned what? We learned tables. Remember the addition tables? You learned how to add 2 numbers. All of a sudden, somebody says, what is the sum of 1, 2, 3, and 4? What is this number? And what we said was, look at, we'll just add these 2 at a time. 1 plus 2 is a number, which is 3. 3 plus 3 is a number, namely 6. And 6 plus 4 is a number, 10. In other words, we essentially did what? We added the first to the second, then we added the sum of the first 2 to the third, the sum of the first 3 to the fourth, and that was how we did this. Of course, what we assumed in doing this was that the sum of 2 numbers was again a number. Up above, we assumed that the sum of 2 functions was a function, and this is not quite as trivial as it might otherwise have seemed. Namely, look at, if you add 2 odd numbers, do you get like things when you combine like things? The sum of 2 odd numbers is always even. You see, you can't say, let's replace the sum of 2 odd numbers by another odd number. You can say it, but it would be wrong. On the other hand, another example, how about subtraction? That's a nice operation. If you subtract a positive number from a positive number, are you guaranteed that the result will be positive? Well, for example, what about 3 less 5? The answer would be negative 2. Positive minus positive can very well be negative. So we must be sure what? That when we combine like objects, we get like objects. And another thing that we assumed was that our answer did not depend upon voice inflection. Now, what does that mean? Let me show you something over here. Look at the expression 12 divided by 6 divided by 2. If you read this as if it said 12 divided by 6 divided by 2, the answer is 1. On the other hand, if you read the same thing as if it said 12 divided by 6 divided by 2, the answer is, what? 12 divided by 3, which is 4. In other words, division depends on voice inflection, whereas addition doesn't. And I simply point out these asides to show you that as we go through advanced mathematical analysis, we are always making use of the same assumptions that we were making when we dealt with more simple things. And I think this is the healthiest way of seeing how our subject develops. We will lead from things that we already know into generalizations that are less familiar to us. At any rate, let's now return to our main theme of mathematical induction and try to summarize what's happened so far. We are working with a certain conjecture, let's call it. The conjecture is that the limit of a sum is the sum of the limits. We know that the conjecture was true for 2 terms. We proved that once it was true for 2 terms, it was true for 3 terms. We then proved that if it was true for 3 terms, it was true for 4 terms. And now if we have any imagination at all, we might become suspicious and say, you know, I think if it's true in general for n terms, it's going to be true for n plus 1 terms. And that brings us to our next stage in our mathematical induction. Namely, suppose the limit of a sum is equal to the sum of the limits in the case that there are n terms in our sum. What can we conclude about the limit of a sum in the case of n plus 1 terms? And without going through the proof here, we'll do these things in our supplementary notes, in our learning exercises, but here I just want to focus our attention on what the main theme is. What we say is, look at, since we can add without worrying about voice inflection, why don't we throw in a pair of braces here, thus reducing our problem to the limit of a sum when we're adding but two functions, use the theorem there, and now, given the limit of the sum of n functions, we know that that's the limit of the sum, and now it appears that the truth for n is going to imply the truth for n plus 1. Now, of course, there may be other problems that work structurally this way other than the limit of a sum equals the sum of the limits. So let's generalize that result. And the generalization is what is known as mathematical induction. What mathematical induction says is this. Let's suppose we have a conjecture. Now, how we get the conjecture is something we'll talk about in a while. But let's suppose we have the conjecture. Well, to try to show that the conjecture is true all the time, we had better be sure it's true at least sometimes. So we say, okay, let's show that the conjecture is true for n equals 1. That's just a simple verification. We show that it's true for n equals 1. Then we say, okay, next, prove that the truth for n equals k implies the truth for n equals k plus 1. In other words, we're not saying that it's true for k. All we're saying is that if it's true for k, the truth for n equals k implies the truth for n equals k plus 1. Then if that's true, our conjecture is true for all whole numbers. Why is that? Well, let's take a look informally here. We know, let's suppose that both of these conditions are obeyed. We know the conjecture is true when n equals 1. Now, take k to be 1. Since it's true for 1, this part tells us it's going to be true for 1 more than 1, which is 2. Now that the conjecture is true for 2, this says what? It's going to be true for 3. And knowing that it's true for 3, this will say it's true for 4. And now I'll loosely use the word etc. and come back and reinforce that as we go along. I think now, perhaps, the best thing to do is to look at a second example. You see, what we did first of all was we used an example to lead into what the definition would be. Now that we have the definition, let's proceed directly to use it. Let me give you a conjecture. The conjecture which I have in mind is that the sum of the first n positive numbers, and this is an interesting formula, it's the last number multiplied by 1 more than the last number divided by 2. Well, let's just see if that's true at all for a while. Look at 1 plus, well, if n is 1, the right-hand side here, the left-hand side here is 1, and 1 times 2 divided by 2 is also 1. If n is 2, the sum of the first two numbers here is what? 1 plus 2 is 3. On the other hand, 2 times 3 divided by 2 is also 3. So at least our conjecture is true for n equals 1 and n equals 2. What does mathematical induction say? Let's take a look again now. You see, we showed that the conjecture was true for n equals 1. And for good measure, we also showed that it was true for n equals 2. So we can check this off. We've done that. Now what do? We assume the conjecture is true for n equals k. That means what? Well, just replace n by k. We're assuming that this is true. From the truth of this, what must we do next? Well, what we must do next is investigate what happens if you add what? Not k numbers, but k plus 1. See, in other words, what happens when you replace n by k plus 1. Now watch how we do this. The same thing that we did in theory before. We say, look, we already know how to handle this amount. We're told that that's going to be k times k plus 1 over 2. So let's rewrite this in this way. Now we can replace the bracketed expression by k times k plus 1 over 2. We add on, of course, k plus 1 because that's the last term that's over here. Now we factor out k plus 1 from this factor here. That leaves us with what? K over 2 plus 1. And this in turn says what? That the sum of the first k plus 1 numbers is k plus 1 times k plus 2 over 2. And notice that that's exactly what the conjecture should say when n equals k plus 1. Namely, what? the sum of the first n numbers, no matter how many you have, is what? The last number times 1 more than the last number divided by 2. The sum of the first k plus 1 numbers is what? It's k plus 1, the last one, times k plus 2, which is 1 more than the last one, divided by 2. And now what we've done is we have verified the second part of our mathematical induction setup. Namely, if we go back to our basic definition over here, we have to show what? Prove that the truth for n equals k implies the truth for n equals k plus 1, which is exactly what we did. And while you're thinking about that, let's take a break for a few more asides, which I think may cement down this idea a little bit more strongly. I mentioned before that induction is something that one uses when one already has a suspicion as to what the right answer is. I don't know how this grabs you, but my own particular feeling is that you do not look at the sum of the first n numbers and say, aha, it's the last one times 1 more than the last one divided by 2. You see, that's the nice thing about textbook problems. When they give you a problem on induction and they say, prove this conjecture, notice that they've already given you a tremendous hint. Namely, they've told you what the conjecture is. You see, in the textbook of real life, one usually has to find out what the conjecture is for oneself. In fact, in the form of a rather interesting aside, there is a very interesting mathematical anecdote connected with this particular problem. It's an anecdote attributed to the mathematician Gauss, who, when he was a young chap, was a discipline problem in school. And the story is that his teacher, as a punishment, asked him to add the first 100 numbers, and Gauss wrote down the answer very, very rapidly. And what he did was, he didn't add these all up. What he observed was what? The first one plus the last one added up to 101. The second plus the next to the last added up to 101. You see? And each pair, going in this way, added up to 101. And how many pairs were there altogether? Why, there were 100 numbers, so there were 50 pairs. In other words, there were what? 100 divided by 2 pairs, each pair adding up to 101. And now notice the recipe, 100, namely the last number, times 1 more than the last number, 101, divided by 2. By the way, in the exercises on this assignment, we have another problem, and that is, if you think this one was already cumbersome, try guessing what the recipe for this one is. What is the sum of the first n squares? In other words, not 1 plus 2 plus 3, etc., but 1 squared plus 2 squared plus 3 squared, etc. I'll give you the answer, but try to think for a while as to how likely it is that you would have conjectured this in the first place. Turns out to be n times n plus 1 times 2n plus 1 over 6. You see, the reason I bring this out is that I call this a contrived example. It is not the case where the mathematician would most likely have invented mathematical induction. The case where he would have invented mathematical induction is the case that we did earlier, for example, where we talk about the limit of a sum being the sum of the limits. You can actually see what's happening, how the truth for k implies the truth for k plus 1. And by the way, let me make one more aside here that I forgot to mention earlier. In our definition of mathematical induction, we said show the conjecture is true for n equals 1. This was quite hypocritical, because the very first example that I picked didn't even start until n was 2. We talked about the limit of a sum being the sum of the limits, and the smallest sum we talked about was the sum of 2 terms. The point that I wanted to mention is, for example, suppose that the first number you can prove the conjecture for is, for example, n equals 7. I don't know why I picked 7. I had to pick something. Let's just call it n equals 7. Suppose I can also show that if the conjecture is true for k, it's true for k plus 1. Then you see what I can conclude is, I can conclude that it's true for n greater than or equal to 7. Namely, if it's true for 7, this says it will be true for 1 more than 7, which is 8. If it's true for 8, this says it will be true for 9. If it's true for 9, this says it will be true for 10, etc. And we go on this way. Now, again, this may be a very naive way of looking at it, but I always look at mathematical induction as a bunch of toy soldiers stacked up in a line, in such a way that if any one of the toy soldiers falls down, he knocks down the one that's immediately behind him. Okay? You see what I'm driving at here? If the first falls, and by the way, that's a big if. If the first falls, he knocks down the second. The second falling knocks down the third falling knocks down the fourth falling down knocks down the fifth, etc. Notice that if the first one doesn't fall, none of them fall. Or for that matter, going back to my previous analogy, if the seventh one is the first one that falls, all the ones behind him fall down. Now be very careful. Mathematical induction doesn't say the first 50 fall down or the first 100 fall down. It says they all have to fall down. For example, here's a case where several fall down, but all of a sudden one isn't knocked down by the one in front of them. In other words, what mathematical induction really involves is the idea not just that something is true, but that it's true because the previous one was true. You see, for example, is it possible that all of the soldiers fall down even though the one in front didn't knock the other guy down? I mean, it's possible all of these go down, but for different reasons. Mathematical induction says much more than that. Mathematical induction says, yes, they all go down, but each goes down because of the one before. And by the way, one more little aside. Notice that in our analog, we assumed that there was a next one. Whatever you say, well, what do you mean you assume there was a next one? Obviously there has to be a next one. But the concept of next depends on whole numbers. For example, when you deal with fractions, there is no next one. Let me show you what I mean by that. Let's talk about the real numbers in general. On the number line, here's 0. What is the first fraction? The first real number, I don't care what you call it. What is the first number which is greater than 0? What is the first number which is greater than 0? And the answer is, there is none. Because whichever one you pick, call it R. Let R stand for the first number which you think is bigger than 0. Okay? How about R over 2? R over 2 is still bigger than 0, but R over 2 is less than R. In other words, given any number you pick that's bigger than 0, you can fit in another one. So there is no number which is immediately next to 0. In other words, as a caution, notice that mathematical induction is used when we're dealing with a whole number of objects. Now, let's emphasize some of these little asides from a more specific point of view. Let me first of all give you an example in which something is true for a whole bunch of numbers, but all of a sudden isn't true in general. Now, how anybody ever stumbled across the example I'm going to give you next, I have no idea, but I find it's a very interesting concept. Let's look at this. Let's write down the following function. P of n, where n is any positive whole number, will be defined to be n squared minus n plus 41. For example, P of 1 will be 1 squared minus 1 plus 41, which happens to be 41. 41 happens to be a prime number, a number which has no factors other than itself and 1. Let's try 2 in here. 2 squared minus 2 plus 41 is 43, also a prime number. Let's try 3 in here. 3 squared is 9, minus 3 is 6, plus 41 is 47, also a prime number. The amazing thing is that as you go all the way through to 40, you get nothing but prime numbers. And you say, it's right so far, it must be right all the time. And this is wishful thinking. This is like the man who wants to count a deck of cards to see if the cards are all there. And he says, 1, 2, 3, 4, 5. Well, so far so good, they must all be here. It's like falling off the Empire State Building, and halfway down, somebody says, how you doing? And you say, so far so good. No, we're in a little bit of trouble here, because as soon as we pick n to be 41, watch what happens here. This becomes 41 squared minus 41 plus 41. And this is 41 squared, which obviously is not a prime. It's 41 times 41. And here's an interesting example where a certain formula generates nothing but primes for the first 40 integers, but fails on the 41st integer. Why did this happen? Because evidently, the fact that this was a prime in no way depended structurally on the fact that this one was a prime. There is our mathematical induction again, that not only must the conjecture be true, but it must follow inescapably from the case before. If you'd like a more fascinating realistic example, it's something that we call the unique factorization theorem of elementary number theory. This says that every positive whole number greater than 1 can be factored uniquely into a product of primes, unique up to the order in which you write them. For example, 2 is already a prime. It's 2. 3 is already a prime. 3. 4 can be factored as 2 times 2. 5 can be factored as, well, it's already a prime. It's 5. 6 can be written as what? 2 times 3. 7 can be written, of course, as 7. It's already a prime. 8 is 2 times 2 times 2. 9 is 3 times 3. 10 is 2 times 5. And 11 is already a prime. Well, this doesn't prove anything. I'm just trying to demonstrate what the theorem says. The interesting thing is, do you notice how n plus 1 factors, I don't know what phrase to use here, but let's call it considerably different than n. In other words, look at what happened to 10 when I added 1 onto it. It factored into 2 times 5. I add 1 onto it, and all of a sudden, the factorization properties change. Let me give you an example. Look at 59. 59 happens to be a prime. Look at 61. 61 also happens to be a prime. By the way, for those of you who are number theory buffs, these are called twin primes. Consecutive odd numbers which are both prime are called twin primes. By the way, 2 is the only even prime, of course, because if a number is greater than 2 and it's even, it's divisible by 2. So 2 is the only even prime. Twin primes are what? Consecutive odd numbers, both of which are primes. So 59 and 61 are a pair of twin primes. One might intuitively suspect, therefore, that the number between them must be sort of a prime too, or whatever that means. Obviously, it can't be a prime, because in between them comes 60, which is in particular an even number. But look at all the nice factors that 60 has. 60 is what? It's 1 more than 59, 1 less than 61, but look at how different it factors. In fact, a pseudo-induction type thing is, look at the factors of 60. 1, 2, 3, 4, 5, 6. We say what, 7? Experimental error? No. But this is not induction, by the way. Notice the fact that 1, 2, 3, 4, 5, and 6 are all factors of 60 does not mean that 7 is going to be a factor of 60. We do not say just because it works so far, it's going to keep working. And I'm not going to belabor this point anymore. Suffice it to say that look at how differently 60 factors compared to the number that came just before it and the number that came just after it. In other words, assuming that the unique factorization theorem is true, the truth for n plus 1 somehow or other has nothing to do with the truth for n. And you see, this is, again, another weakness of what's called induction. Well, so that's a weakness of induction. The point that I'm making is, why shouldn't induction have some weaknesses? After all, if it could solve every problem, what we would do is have a calculus book that was 3 pages long. It would be called The Principle of Mathematical Induction. When we solved that problem by induction, everything else would be done. No, there are problems that do not lend themselves to induction. In summary, induction is a particularly effective technique which one uses to prove that something is true for all whole numbers, provided that one has a suspicion that this thing is true in the first place, and secondly, that even if the suspicion is true, the truth for the n plus first case follows inescapably from the truth for the nth case. At any rate, this completes our lecture for today, and until next time, goodbye.
Funding for the publication of this video was provided by the Gabriella and Paul Rosenbaum Foundation. Help OCW continue to provide free and open access to MIT courses by making a donation at ocw.mit.edu/donate.